Hi, welcome. Welcome to everyone. I'm Alessandro Massolfini and I work in the numerics group, and today I'm going to talk about hyperelasticity and how to model hyperelastic material. Hyperelasticity represents a wide class of material which can undergo to extremely large deformation and still remain fully elastic. Everything that I'm going to show you today is taken from the hyperelasticity and solid mechanics monograph that you can find in the documentation. Today I'm going to briefly introduce the hyperelasticity and how to model hyperelastic material and what we need to model solid mechanics problem and all the new features that we introduced for version 14 of Mathematica. Then I want also to show you some simple example that show you how to implement this solid mechanical problem, and then I want to show how we can use hyperelasticity to model some multiphysical problem. First of all, in the field of solid mechanics and then of the hyperelasticity, we need to describe the displacement and the deformation of material. So the dependent variable that we need is the displacement. We can describe displacement in both one, 2, or 3 dimensions. To remain as general as possible, we can express this in 3 dimensions with 3 different variable u, v, and w. Each of one depend on the independent variable x, y, and z. Of course, we can have time-dependent problem, but today we are going only to talk about a stationary problem, and of course we need some material parameters to represent different material. We can now see two different configurations. The reference one expressed with is omega 0 with the local coordinates big X, and the deformed configuration of or current configuration is omega and is function of the displacement map phi, and to map the surrounding of the big X to the small x in the current configuration, we need the deformation gradient that is mathematically expressed as the identity matrix plus the gradient of the displacement. To represent the physical phenomenon behind the deformation of the body, we need some equation. Of course, the mechanical equilibrium equation that is a partial differential equation, and now we can express this in both the reference of the or in the current configuration. They are two different equations, but representing the same physical behavior and the same phenomenon. But we need to map the coordinate between one configuration and another, depending on the deformation of the body. And for the same reason, we can now have different stress measures, like the Piola-Kirchhoff one or the Cauchy stress, but they are both the stress inside the material, but we can see different expression of the stress in the reference configuration or in the current configuration, and they are linked from a coordinate mapping. Then we also need some boundary condition in order to close the problem and be able to solve. And of course, we need a material behavior which represent the relation between the deformation of the material and the stress in the material. And this is where the hyperelasticity comes out. We now, in the hyperelasticity framework, we are able to describe the material as depending on a potential which represent the strain energy of the material, so the energy that the material needs to deform, and we can express the stress as the derivative of the strain energy with respect to a strain measure, like the deformation gradient. For instance, in this chart, we can now see a very nonlinear relation that link the uniaxial stress and the uniaxial stretch. This is a uniaxial tensile test example, and this sample is stretched like 3 times the original size, and we can see this nonlinear relation that show different behavior by increasing the stretch. And this is an example taken from the EO model. So in the version 14, there are some news about hyperelasticity. We introduce several isotropic material model with the possibility to model nearly incompressible behavior, and also for the bidimensional cases, the plane stress and the plane strain model form. Then we also introduce the transverse isotropic materials with the fiber reinforced example, and the possibility to model the different material law to experimental data of tensile or compression test. Then we also introduced the possibility to use the multiplicative decomposition of the deformation gradient to represent different physical phenomena. And we described this in new application example that show you how to start and how to implement also complex deformation. Everything is inside the documentation, mostly in the hyperelasticity monograph and in the linked page. Now I'm going to talk a little better about some of this point. So we introduced different material model, some phenological model like the EO, the Muller-Rivlin, 2, 5, or 9 parameters, some mechanicistic model like the Nukan or the Arruda-Boyce, and some hybrid model like the GAN. They are based on different strain energy, of course with different material parameters, which correspond to very different behavior. For instance, this chart is extracted from the hyperelastic model comparison example that show you how to calibrate your different material law on experimental data, and we can also see how these different models show very different nonlinear behaviors outside the fitting range. We also introduce some reinforced material, and these materials are described by splitting the strain energy into an isotropic part, which represents the bulk of the isotropic matrix of the materials, and is described by some of the strain energy that I introduced before. And then we have this contribution of which represent the fiber and depends on the fiber orientation and on the fiber stiffness. For instance, we can see this plot by fixing the fiber stiffness and varying the fiber direction, we can observe very different behavior of this unit square that is fixed to the left and to the right. By varying the orientation, we can see very different deformation. Then we introduce the kinematic decomposition that allow us to split the deformation gradient into an elastic contribution, which represent the hyperelastic material model deformation. And then we can also include some inelastic strain within the inelastic deformation gradient that we can use to model several phenomena like the thermal expansions or plasticity or some growth of soft tissues. I'm going to talk a little better about that in the following slide, but I want first to introduce an example. We can start with a very simple example of this rectangle of size 1 by 2, and this is fixed to the left and pulled to the right. Of course, to describe this problem in the solid mechanics world, we need the displacement variable u along x and v along the y direction, both depending on the spatial coordinates x and y. Then we want to model a Newton material that is based on this law. And to model this material, we only need to specify inside the parameters variable the solid mechanic material model association within the Newton isotropic name, and of course, the material parameter that for the Newton model is the shear modulus. Then we can define the domain omega. That is basically a rectangle with size 2 by 1, and then we can include some boundary condition. We need to express the load that is a Neumann boundary condition, and to do that, we can use this the built-in function solid boundary load value. And we apply this function where on the right side where x is equal to 2, and we specify this is like a function as a function that take f as an input, the force, and uses this input to express F Newton as a force along the first coordinate, which correspond to the x, to the horizontal direction. Then with solid fixed condition, we can express the fixed left side where x is equal to 0. Then we can express the model. To express the model, we need to write the equilibrium equation, and we can use the built-in function solid mechanics PD component that allow us to express the equilibrium equation. And it's very useful to use this built-in function because manually the equilibrium equation could be very, very long and complex because now we are representing very nonlinear behavior. So we can use this built-in function to express in a very compact form this model, which take f as an input and use this input to express the boundary load. Then with this, we have now defined the model, and we can use this to solve the problem. We only need to describe the force and use this force to express the model now, and we can use this solve value to solve the problem. And then we can observe this displacement field that now it's very large displacement, which is more or less 3 times the original size of the rectangle. And of course, we can also increase the external load from 12 kilonewton to 20 kilonewton and solve with the same procedure the problem, and we can see a displacement, a larger displacement now that is around 6 times the original size. And we can also try to increase another times the load from 20 to 40 kilonewton, but this time we can observe an error with the solution because now we are trying to apply a very, very large deformation, which leads to the model far from the convergence. So to solve this problem, we can use the parametric solve and express now. We can express the force with respect to a parameter p that represent a scaling factor for the load, and we can iteratively solve this problem by gradually increasing the load from 0, the scaling factor from 0 to 1, so the force from 0 to the maximal force. And for each solving step, we can use the solution of the previous step as an initial seeding for the actual solution. And with that, we can solve also for this very, very large displacement of 13 times the original size. Starting from this simple model, we can introduce several other behaviors. For instance, we can introduce some fibers to reinforce the materials. And to do that, we only need to specify the fiber's direction. We start from the same new anisotropic description for the bulk contribution, for the isotropic contribution, and then we add some fiber. And to add the fibers, we only have to specify the reinforcement stiffness factor, which link the fiber stiffness to k times the stiffness of the isotropic material. And then we need to specify the direction of the fiber. With this specification inside the parameters variable, we can follow the same identical procedure to specify the model in function of the boundary force, and then specify the force and solve the model. And now we can see a very different displacement. This is the same example, fixed to the left, pulled to the right, and then now we can see a smaller displacement and a very different and non-isotropic displacement. Starting from the same example, we can now try also to use encouple this problem with the different physical phenomena, we can use the kinematic decomposition to split the deformation gradient into the elastic contribution, that is the same deformation that I described in the previous slides, and then add some inelastic contribution that we can use to describe several inelastic deformation like the thermal expansion, the hygroscopic swelling, the plasticity problem, or some growth of biological tissue. For instance, thermoelasticity link the hyperelastic material with the deformation induced by temperature, which that we can represent inside the thermal inelastic deformation gradient, defined as the identity matrix plus the thermal strain. Thermal strain is defined as the differences between the local temperature and the reference temperature scaled with the thermal expansion coefficient alpha. We can also use these thermal PDE models, thermal strains built-in function to express this thermal strain, which represent the deformation induced by the temperature. We know that material expand when temperature is higher than the referential values, and with the opposite situation when temperature is below the reference temperature. So we can set up the same rectangular example with the new kinesiotropic model, and we only need to specify inside the inelastic deformation gradient parameters and link these parameters to the thermal inelastic deformation gradient that I defined in the previous slide. So we need also to specify other parameters to use the built-in function for the thermal strains. In particular, we need to specify the temperature, that is T function of X and Y, the reference temperature 25 degrees, and the thermal expansions that basically is a number, but it could be also a function. We can, and it is done in the monograph, link this problem with the heat equation and solve a full coupled example. But for now, in this presentation, I want to manually define the temperature with like a simple file which vary only on the vertical direction from 10 degrees in the bottom side to 100 degrees on the top side. This is the temperature file, and by applying this temperature, we can set up the same with the same procedure, this model. Now the applied force is 0, but we still need the parametric solver to gradually apply the thermal load. So we can solve this problem with this parametric solver, and in the end, we can observe a very different displacement field now. Beside the force being 0 now, we can see this deformation and an expansion to the top side and this contraction on the bottom side, which lead to a generally bending of this rectangular sample. We can, of course, use this inelastic contribution within different physical phenomena, and it is described in the monograph with several other examples. As I mentioned before, everything that I show you today is inside the hyperelasticity monograph. I really suggest you to have a look to this, to both the hyperelasticity and the solid mechanic reference page to have a better idea on how to model this solid mechanical problem. I want also to thank Oliver, which drive our numerics group, and Martin. He isn't here to present, but he had done a lot of work on the fiber reinforced and the transverse isotopic materials. So my presentation is ending now, and feel free to ask everything you want to ask about hyperelastic and solid mechanical problem. Hi, yes. Harald, so the current limitations are mostly about the model size, number of elements, and it's not a real limitation, but of course, for very complex problem due to the linearity, you need to iteratively solve the problem with a very small step. This will, of course, require a very long solving time. Other limitation could be to the multiphysical coupling, because we need to a different law to couple with different phenomena, and now we can mostly model the physical interaction that I mentioned before. But of course, this is in development for include different other phenomena and to include different field of physics within this solid mechanical deformation. Yes, to search for the hyperelasticity monograph, you can search in the documentation for the PD models monograph, and then this is linked to the hyperelasticity monograph, or you can search into the Wolfram mathematical documentation for directly for hyperelasticity on solid mechanical monograph. You will, of course, find the documentation page that I mentioned.